அது ரைட்டு தான். குழம்பும் கிரேவி
Hello. Okay. சரி இப்போ வந்து அந்த ஃபில்டர் போடு.
the graph. And in our case,
பண்ணி பாரு.
the graph is finished running. You can see the full states printed out here. So you can see if you look at this messages key in our state snapshot,
இதுல
it
இருக்கும் பாரு டேட்டா. டாட் ரெஸ்ட்னு ஒரு ஃபைல் வச்சிருப்போம் பாரு அதுல பண்ணு.
has this whole set of messages, which we can look at here. But this snapshot has a few other nice things. It has some metadata. It has, for example, the next node to go to. In this case, there would be no next node because we've terminated the graph. And you can see things like checkpoint ID. So that's the first thing to note is that this graph.getState
ஆ
gets the state of the graph at a given point in time, and you can look at it. But you can do more than that. You can actually use this get state history to look at the history of states at every step
ஏதோ
that your agent
பட்டன்
took.
கிளிக்
So
ஆகுது.
let's go ahead and do that. We can look at the length of this. So there's 5 steps. And let's look at the ordering. So this first is actually looks pretty similar to this. So the first element in this list is just the current state, and you can kind of go back in time. So this was the start of our agent. So this is just the start node, and then we can look further. Boom. There's our human input and so forth. So we have the whole state history at every step of our agent captured using this graph.getStateHistory. It's pretty nice. So let's visualize this to build a little bit more intuition about what's going on. Here's a toy graph, 2 nodes. So here's the control flow. I start, go to node 1, node 2, and then end. And I modify the state as I go. So your graph is just the control flow you laid out of nodes and edges. Now the steps, or super steps as they're technically called, are just basically every sequential node is its own step. And that's what we've been working with for the most part. Now parallelization is something we'll introduce a bit later, and parallel nodes also run as the same step, but in this case these nodes are sequential, so they're separate steps. Now checkpoints just wrap the state and relevant metadata at every step. So these state snapshots just serve as checkpoints. That's it. Pretty straightforward. And as noted, state snapshot is just a type for checkpoints, so that's cool. Now we saw above, when we call graph.getState, we get the current and most
பட் டியூபர் போ. கைஸ் ஒரு பிபிடி ரெடி பண்ணுங்க கைஸ். சரி முடிச்சிட்டு பண்ணணுமா? ஆனால் சார் 2 செல்லு யூஸ் பண்ணுறாங்கிறேன். 2 செல்லு யூஸ் பண்ணுங்கிறேன். இதுதான் டெஸ்ட் பண்ணல. செல்லு நோண்டிகிட்டே இருக்க. 2 செல்லு யூஸ் பண்ண சொன்னேன். சரி ஏதோ கேட்கணும் தான்டா. இல்லை இல்லை அதெல்லாம் இல்லை. ஒன்றை யூஸ் பண்ண சொன்னேன் ரெண்டுத்தையுமே.
ஐயோ ஒரு 5 நிமிஷம் இதெல்லாம் தப்பு. எப்படி தெரியாது அந்த செல்ல காமி
இங்கே அப்படியே இரு.
நான் நல்லாவே இருக்காது.
நான் எடுத்து டெலிட் பண்ணிடுவேன். ஏன் அப்படி பார்க்குற? நல்லாதாம்மா இருக்கும்.
சூப்பரா இருக்கு.
100 சார்ஜில் வச்சுருந்தா தாங்கும். 100 சார்ஜில் வச்சுருந்தா தாங்கும். ஆனால் நான் என்ன பண்ணிட்டேன், பேட்டரிக்கு வந்து 80 மட்டும்தான் ஏறுற மாதிரி வச்சுருக்கேன். அதுவே வச்சுக்க, அப்போ பேட்டரி ரொம்ப நாள் இருக்கும். பேட்டரி எடுத்துக்க,
என்னதான் ஆச்சு?
சார்ஜ் ரொம்ப நிற்காதுமா அந்த செல்லு மாதிரி. பேட்டரி மாற்றலாங்கிறேன். நான் என்ன சொல்கிறேன், பேட்டரி அதோட இது வந்து கேமராவுக்கு மட்டுமே வச்சுக்கலாமா, ஃபோட்டோ கிட்ட எடுக்க.
செல்லு வாங்கி கொடுக்கறப்ப செல்லு வாங்கி கொடுத்து.
அவர் கேமரா மாற்றிருக்க மாட்டார்ல, அவரு டிஸ்பிளே விட தானே மாற்றுவார், கேமரா மாற்ற மாட்டார்ல. அப்படின்னா அதான்
என்ன மாத்தி கொடுத்தாரு?
டிஸ்பிளே தான் மாற்றி கொடுத்தாரு.
டிஸ்பிளே தான் மாத்தி கொடுத்தாரு.
அதோட நான் வந்து சொன்னேன் இந்தமாரி.
எவ்வளவு இது?
இது நான் 5600
ஒரிஜினலா?
ஓரளவுக்கு ஒரிஜினல்.
டெம்பர் போட்டியா?
டெம்பர் போடல, அவர் வாங்கிட்டு வரனாரு.
டெம்பர் ஒரு கவர் போட்டு விட்டு. இது கவர் இருந்ததுல
அங்கே கடந்துருக்கும். ஆமாம், வீட்டில் தான் இருந்துச்சியா?
அப்பாவதான் கொண்டாந்து என்கிட்ட கொடுத்தான்.
இல்லைம்மா, கடன் தூக்கி விட்டேஞ்சிட்டோம்.
அம்மா காலேஜ்
இதனால நெட்டு ஃபாஸ்ட்டாக இருக்குடா. அதில் போட ஒரிஜினல்லே போடு. நான் ஒயர் தரேன்டா. வைஃபை ஸ்பீடு எங்கே வைக்கும்? என்னாச்சு ஆ இது ஃபில் பண்ணிட்டேனா பிஸ்னஸை ஆமாம் இதாயிடும் நம்ம செஞ்சிடும் மெயில்
சாப்பிட்டு 11:45 தான் நீ சாப்பாடு கேட்கணும்.
இதாயிடுச்சா இந்த பேஜ் பேங்க் ஸ்டேட் ஆயிடுச்சு பேங்க் ஸ்டேட் ஆயிட்டா எப்படி யூஸ் இது வந்து பேங்க் இதாகும் இதாயிடும் யூசர் போட்டுக்கிறா யூசர் என்ன சரி இப்போ இதை வச்சு இந்த பேங்க் வச்சுனா நம்ம அது இருக்கலாம் இப்போ யூசர் கிரியேட் பண்ணி அதுதான் யூசர் கிரியேட் பண்ணா எப்படி பண்ணிக்கிறீங்க லாகின் பண்ணுங்க ஆமாம் சரி 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 யூசர் கிரியேட் பண்ணி கான்டாக்ட் யூசர்ஸில் யூசர்ஸ் ஹலோ எஸ் ப்ரோ யா ஓகே வாட் டு யூ மீன் பிஸ்னஸ் லாகின் that is no problem, right? Because whatever email they give, it will go. Okay. Business account, it's not working, you are saying. I don't know. Let me check once, bro, and I'll tell you. Okay, I'll call you. I'm actually working on the code. I will test it and call you. Okay. In your code only. Oh, there it is different and just okay. Huh. Okay, bro. I'll do some research, like if it is possible or not. I'll tell you. Okay. Okay, bro. Okay. Okay, bro. Okay. Okay, bro. ஏதோ புதுசா ஏதோ சொல்றான் பைத்தியம். ஆட எதுக்கு தெரியலடா, அவன் ஆப்பே பண்ணிட்டு இருக்காங்க. அதுதான் அதெல்லாம் காட்ட மாட்றான். ம். ரோஷினி சார் எங்க போனாங்களா? எங்க இப்பயா? எங்க? ஆமாக்கா, அங்கே இது அட எங்க என்ன சொல்ற? ஏன்டா என்ன சொன்னானா? ஆமா. ஆ. அப்புறம் ஆ ஆ ஆ இது தானாவே வரும்டா. ஏன் வேலை செய்யலையா? அது வேலை செய்யலைன்னா என்ன பண்ணு? எதுவுமே ஏன்னா எல்லாத்தையும் அளவு ஆள் கொடுத்த அளவு நீ ஒரு அத்தன்டிகேட்டர் கொடுத்து வச்சிருக்கிற. ஏஜென்ட்டா அதில் வந்து டோக்கன் லாகின் இருக்குறா, டோக்கன் அப்டேன் பேர் அதான் லாகின் கொடுத்து டிவைஸ் கியா வந்துட்டு பழைய கோர் இருக்கக்கூடாது. யூசர் ஐடி தானே பண்ணும். பழைய கோர்ரா இது. மாத்தி விட்டியா? யூசர் ஐடி தான். ஆமாடா டிவைஸ் கீ வந்து அந்த டிவைஸ் ரெஜிஸ்டர் பண்ண. இல்ல அங்கேருந்து தான் வரும். அங்கேருந்து தானே வரும். டிஃபால்ட் தான் சொல்றேன். மெயில்ல இருந்து வரும். ஆக்சுவலி ஃபார்ம்ல வாங்குறாங்கடா, அது அட்மினுக்கு வந்து வாங்க மாட்டாங்க. யூசர் வந்து மேனுவலாக கிரியேட் பண்ணுவாங்களே, அப்போ வந்து யூஐல இருந்தா வருது. ம். நீ ரோஜா நான் முல்லை என் கையில இவன் நெல்லு. ம். நீ ரோஜா நான் முல்லை என் கையில ஐபோன் சொல்லு. என்ன பண்ற?
recent checkpoint. Graph.getState history, we get the list of state snapshots or checkpoints that the graph has executed. Now let's talk about this notion of replaying. So we can actually replay our agent from any of its prior steps, and it's pretty straightforward. Let's think about it like this. When we run graph.stream, we pass in none, but we give it a thread ID. It just picks up from the current state in the thread ID. We've actually seen that before. Pretty straightforward. Now, what if we just pass in a checkpoint ID along with the thread ID? In that case, the graph will kick off from a particular checkpoint. So it's a subtle difference, right? If you pass in just the thread ID, it'll just pick the current state of the thread. If you pass a thread ID and a checkpoint ID, you can rewind to any checkpoint within the thread. So here's a toy example. Let's say I pass in, if I just run graph.stream with a thread ID, it picks this blue guy, the most recent state snapshot, and runs from there. In this toy example, nothing would happen because it's finished. So it's a subtle but important point to make here. When I pass in a checkpoint ID that the graph has already executed in the past, we actually replay, we don't re-execute, which is to say, we just play back through those checkpoints because the graph knows, hey, I've already executed this in the past. So this is known as replay, okay? So let's just say we pass this red checkpoint here, we would replay the graph from red to blue and then finished. So let's go ahead and give that a shot now. In our agent example, let's just pick one checkpoint that we want to look at here. So this is the human input. We can see the state at this input. We can see next, so this indicates the next node to go to. We can also look at the config, which contains the thread ID and the checkpoint ID. So to replay, all we need to do is just pass that in. This replay.config contains our checkpoint ID and the thread ID, and we just can run from there. There we go. So you can see it's very fast because we're not re-executing anything. We're just replaying exactly what happened from that human input. And we can see we went to the AI model, which returns the tool call, tool node, back to AI, and we're done. So that's just a simple example of replaying from a specified checkpoint in your state history. Now let's talk about the idea of forking. So we've actually run this already. When we call graph.updateState, you pass in the thread ID, you pass in the state that you want to update with, you actually create a new checkpoint. But you're just creating a checkpoint on whatever the current state is. So you can think about this as you're just forking the current state, and you're adding that as a new checkpoint to the history. Easy enough. Now, there's an interesting thing I can do, though. What if I want to rewind and fork a prior checkpoint, not just the current one? You can do that. All you need to do is update state, pass the checkpoint ID in, and this is in our cartoon here. If you kind of go back again, we're looking at this kind of like little two-step graph, right? Let's say I want to go create a fork from that first step. Well, I can do that. Just pass in that checkpoint ID, and now I have a forked checkpoint that I've created. Now, let's talk about something interesting here. If I call graph.stream with this forked checkpoint ID, what happens? This has not been executed before. LangGraph knows that, and then you actually re-execute your graph with this fork checkpoint, which makes a lot of sense, right? So it's a very subtle thing, but important to understand. Replaying versus re-executing. If I pass in this red state snapshot, okay, my graph knows I've already run this. I've already executed it before, and it replays. If I pass in this purple state snapshot, the graph knows this has never been executed before, and it actually re-executes. It re-invokes the chat model. Let's see that right now. So let's fork that same, in this case, it is the human input, okay? The checkpoint that contains the human input.
Branch என்ன கோடு யூசர் கிரியேட் பண்றப்பையும் கேட்கணும்ல இல்ல யூசர் கிரியேட் பண்றப்ப கேட்க சொல்லு ஒரே தெரியாம முடிஞ்சிடும் அப்பதான் யூசர் கிரியேட் இப்ப பிரான்ச் நிறைய பிரான்ச் இருந்தா என்ன பண்ணுவான் இல்ல இல்ல அப்படி கிடையாது ஒரு பிசினஸ்க்கு ஒரு அட்மின் ஆமா அவன் பிரான்ச்சே போட்டுரு சரி சரி
But in our agent, we have the configuration, no problem. We have our thread ID, we have our checkpoint ID. Now, let's just call that update state, just like we saw up here in the cartoon. We'll call update state, and we'll pass that to-fork config, which just contains the checkpoint ID. And, okay, here's something I want to explain a little bit carefully. We're going to pass in a new message. So we're going to say multiply 5 and 3, okay? But what we're going to do is, so again, we're replacing 2 and 3 with 5 and 3, so that's cool. But what I'm going to do is also supply the ID of my message from the initial checkpoint. And what that's going to do, it's just going to overwrite it. Okay, now why is that? Let's think a little carefully here, okay? This is subtle. The messages key uses that add messages reducer. We've talked about this already. The reducer will append new messages to a list. So if I didn't supply this ID, it would append this message to this one. And I'd have an updated state with 2 messages, 2 human messages in a row, okay? Now I don't want that. I actually just want to overwrite this existing one, okay? And to do that, all I need to do is pass the ID, and then it'll be overwritten, create a new checkpoint. So subtle thing, but something to remember. When you're doing update state, remember what state key you're updating, and what's the reducer on that state key. In this case, the reducer is add messages, which will append unless you supply the ID, in which case it will overwrite. Nice. Okay, so we got that clear. Let's make that update. Now we have a new config. We have a new checkpoint ID. Okay, remember this last one ends in 13, this one ends in 66. Okay, cool. New checkpoint ID. I want to show you something else. This is interesting, right? Let's look at our states. Now, okay, we've made a few different updates. So now there's actually 9 states here, okay? We've updated this a few different times. And previously, when we first ran, remember that above, there's only 5. So what's happening is, as we're calling update state, we're actually adding new forked checkpoints to this list in our thread. Let's look at our diagram. Our thread is just a collection of checkpoints. We're calling update state, and we're creating new forked checkpoints, and they're just getting added to the thread. That's it. Cool. So we can look at our current state. There it is. Multiply 5 and 3, exactly as expected from our state update. That's good. Okay, you can confirm that by looking at the messages. Yep. We can look at the current state. Yep. So again, the current state will match the first value in our state history. So we're looking good here. Now let's rerun with our fork config. Okay. The fork config supplies this checkpoint ID that we've modified. Let's confirm this works. Perfect. So we've modified that human input. 5 and 3, the tool call, 5 and 3, 15. The output's 15. Very nice. Now let's look at the current state. And it's been updated to have this full list of messages resulting after the agent runs. So we've just been able to fork a specified checkpoint and rerun our agent with that fork. Now let's look at time travel using the LangGraph API. Just like we talked about before, our agent's deployed locally to Studio. We have the URL here, and we can connect to it just like we show here. Now let's talk about replaying. So first, let's do an initial run of our agent from scratch. Again, I'm just going to stream updates. I'll pass in this human input, and let's kick that off. So here's my agent running for the first time. Human input, tool call, tool node responds back to the assistant. Same as we've seen a lot. So this is just my initial run. Now I want to replay from one checkpoint in that run. So all I need to do is get my thread history. This gets my list of states, and let's pick a state to replay. Cool. So this is just that human input. You can see that's the only thing here. The next node calls the assistant, just like we have seen before. So this is great. Now let's just replay from here. So all I'm going to do is, the only new thing is this checkpoint ID. I just pick the checkpoint ID from my replay config. So this config has a checkpoint ID. Boom. Just pass it in. Supply none. And it'll just start replaying from the checkpoint. Remember, it replays because it already knows this has been executed. I'll use stream mode values. This will stream the full state at every step. Let's give it a shot. Cool. So we'll reemit the current state. Good. Multiply 2 and 3. And we just replay what we did. Very good. Tool call. Tool node. Final response. Very nice. So it's like we showed before. It's pretty simple. The only new thing to track here is to replay from a particular checkpoint, just apply the checkpoint ID. That's really the only new thing here. Likewise, we can replay by streaming updates. Just only a minor aesthetic difference. In this case, we only look at the updates to state, assistant node, tools node, assistant node. So easy enough. We've seen this quite a bit before. Now let's show forking. So let's do what we did before. Rerun from scratch, new thread ID. Cool. Human input, assistant, tool call, tool node runs, back to the assistant. Now let's pick a particular checkpoint we want to fork. So same as before, we'll look at the human input, multiply 2 and 3. And we can look at this is the message ID for this particular human input. And we'll see why we're going to use this in a little bit. Let's just confirm to call next as assistant, and the checkpoint ID we also have. These are all the raw materials we need. Now, all we need to do is just edit the state. So remember, we're modifying the latest state in our messages key. And message key uses the add message reducer, and this will overwrite a message if you supply the ID. So all we're going to do is call messages, update state on messages. We'll supply a new message in, so in this case, multiply 3 by 3. We'll supply the ID of our existing message, and it'll overwrite this. So we'll overwrite 2 and 3 with 3 and 3 because we supplied the ID. And then we just call update state, again, supply this forked input right here, supply the checkpoint ID and the thread ID. There we go. Now we have a new forked config. So this is basically a new checkpoint, okay? And we can look and see, if we look at the state history now, this new checkpoint has been added. Perfect, look at that. Multiply 3 and 3. So it's a new checkpoint that's been added. Now this is our current state. Now we just rerun from here, this new checkpoint ID. Now because the graph knows that this has not yet been executed, we're actually going to re-execute or rerun every node in our graph following this one. So you can see the next node to call is going to be the assistant. And you can see right here. And let's go ahead and run that. Very nice. Tool call runs with these forked arguments. Tool node executes it. Final response, 3 and 3 is 9. Perfect. So this shows forking with the API. Very similar in concept to what we did previously. So now let's have a look at forking in Studio. I'll go over to Studio. So here we are. Here's our agent. We have a fresh thread. Let's just kick this off. Multiply 2 and 3, just like we've seen quite a bit. Let's run it. Nice. There we go. So this is our first run. Nice and easy. Now let's say I want to explore the result of different tool calls. Let's add an interrupt at my assistant. Now I can go over here and see this edit. I hit edit, and I can just modify the payload here if I want to. Cool. 4 and 4. Now all I have to do is just run this fork, and it's going to run from this particular state forward in my graph with this updated output. Let's give this a shot. Cool. So what happens is now I've gone to my tools node. I see, okay, here's the updated tool result of 16. It's gone back to my assistant, which I've paused. That's why we're paused right now. Nice. I can do that again. Let's just say I want to examine different tool calls here. 8, fork. Again, I can look at the tool result. 32, cool. Now, with a simple graph like this, there aren't too many places where you actually want to fork and explore alternative trajectories. It's very basic. It's only effectively, just iterating between the assistant and tools node. But if you have a more complex graph with many steps, there may be many places you want to interject and fork the state to explore alternative trajectories. It's very easy to do in Studio. In fact, in some ways, using the UI is almost easier than using, for example, the SDK. So I often like to do kind of exploration of alternative trajectories here in Studio rather than just with the API in this particular case. So this is a very good thing to be aware of. If you want to play with and explore alternative trajectories, forking in Studio is a really nice way to do that.
By now, you've learned a lot of useful foundations. You understand what agents are, you understand the core LangGraph abstractions, you know how to use memory with LangGraph, and you also know how to incorporate human in the loop. With these foundations in place, it's time to bring them all together to create your AI assistant that can actually do useful work for you. In this module, we'll first introduce the idea of AI role play. So that is creating personal assistants with specific sub-goals related to your overall task. We'll discuss controllability features in LangGraph, such as parallelization and subgraphs, that allow you to take these personal assistants and perform knowledge gathering with various external tools like web search or document retrieval across all the subtasks you've given them. We'll also cover MapReduce in LangGraph to parallelize this entire knowledge gathering process across all of our assistants, which speeds up the process considerably. We'll show how to distill this gathered knowledge into customizable outputs, such as reports or wikis. We'll then use human in the loop to review those outputs and finally connect LangGraph to external reporting tools like Slack. Collectively, this will produce a general purpose assistant that you can use for many different things that you do in your daily work that are boring or tedious. This could be like summarizing meetings. This could be gathering information on partners that you need to meet with. This could be writing social media posts. This could be distilling your internal documentation into wikis. Really, our aim here is to introduce these ideas and foundations so you can actually take this assistant and customize it to automate boring or tedious parts of your daily work.
In Module 3, we went in depth on human-in-the-loop workflows. We talked about 3 popular use cases, including human approval of certain actions for an agent, like tool use, debugging through things like time travel, where you can go back and replay or fork prior states, and also editing state. So we're actually going to move now into a new module that ties together these themes with a few other ones related to controllability and multi-agent workflows. And we're going to kind of build all this into a pretty interesting multi-agent research assistant that will kind of tie together all the aspects of the course. Now to start, we're going to talk about a few controllability topics, and let's start with parallelization. So the main idea here is fanning in and fanning out is something that we often want to do in graphs. I'm just going to define a really simple graph here. Okay, this is something we've kind of looked at before. Here's just a linear flow, A, B, C, D, right? I have a single state key, and if I run this, what happens? Okay, so as we go from A, B to C to D, we just overwrite the state at each node. So that's fine, that's simple, and we've talked about that a little bit before. Now let's say we actually want to run, for example, B and C in the same step. Let's just go ahead and build a graph that does that, and all you have to do is just create an edge from A to B and A to C. And that's it. And then B to D, C to D, D to end. So this is actually doing fan in and fan out, in the sense that we are fanning out. Let's just draw it out to show you. We're fanning out from A. So we're running A as a step. We're running B and C together in the same step of the graph. And we're running D as a third step. So let's go ahead and try to run this. And I'm actually going to catch any potential errors to highlight something interesting to you. So you're going to see an error occurred at key state, can only receive one value per step. So what's happening is B and C are both trying to update state in the same step, which is ambiguous. If you think about it, both B and C, think about it simultaneously, are writing to the same channel or same key in the state. So the graph doesn't know which one to actually keep or use. So this brings up an important point about parallelization, which is that if you're running certain nodes in the same step, i.e. in parallel, and they're writing to the same channel or key, you need to use a reducer that can aggregate those updates. We talked a lot about custom reducers. We talked a lot about reducers in general. So let's just do something simple. Let's just define state with a reducer that will just add updates to a list. And now we're going to draw that same graph. Here we go. So we're going to fan out. We'll fan back in. So now nodes B and C will be updating this state key, but fan out, we'll fan back in. So now nodes B and C will be updating this state key, but because we have a reducer, all these state updates will just be appended to the list. So let's give this a shot, make sure it works. Very nice. So we can see we just get this list of elements, and we're able to run steps B and C in parallel, because even though they're writing to the same channel or key, we have a reducer that handles those updates and just appends them to the list. So the key point to remember is when you're doing parallel node operations and you're writing to the same key or channel in your state, just be very careful and make sure you're using a reducer that can actually handle those simultaneous updates. Now let's walk through another common architecture in parallelization. We'll go ahead and draw a graph out here. We'll modify it slightly. We're going to show 2 branches here. Now one branch has 2 steps and the other only has 1. So what's going to happen? What you're going to see is that even though steps B and C will be run roughly at the same time, that is, they're the first step in each branch, we will wait to run D until everything in this other branch is completed. Now let's go ahead and see that right now. Nice. So we can look at the final state list, and what we can see is first A writes the state, then B writes the state, then C writes the state, and then B2 writes the state. So even though we ran C, we don't go ahead and run D. We wait for everything in this other branch to finish, because these are all run, that is B, B2, and C, are all run as part of the same overall step, okay? So you get B, C, and B2 all updated before D updates the state. So it's just an important point to remember that when you have parallelization, these parallel branches of your graph are run as part of the same step, and we will wait until they all finish before running D when they fan back into. So let's look at the state after our graph ran. We have A, B, C, B2, and then D. So you might ask, well, why is C coming before B2? Okay, they run as part of the same step. So you can see B here, C here, B2 here. And the answer is, this order of updates is actually set by the graph. So LangGraph decides how to order these updates when they're within the same step. You don't have control over that. But what if you want to customize that? So we can do that pretty easily using a custom reducer. Let's define a reducer that's actually just going to sort the values in our state after each update. So it's pretty simple here. You can see we basically perform the concatenation, and then we just sort the values in the list. So it's pretty simple. So recall the ordering above was B, C, then B2. And now we're going to find that same graph. Cool. Let's run it. And now you can see A, B, B2, C, D, because our reducer actually sorts the values as they're added. So even though by default, we don't have the ability to control the ordering of these updates within the same step here, we do if we supply a reducer that will control or manage the order of those updates as we make them in the state value. So let's pull all these threads together into a realistic example, which we're actually going to end up using a bit later as well. So it's kind of a nice little precursor. So I'm going to define an LLM. I'll use OpenAI just like we've been before, but of course you can use any model you care about. I'm going to define a really simple graph here. So here's my state. It's going to have question, answer, and then context. So you're going to see context is a list, and I have this add operator, which means we're going to append to it, okay? So this gives you a clue that this context thing is probably what I'm going to be writing to in my parallel nodes. That's just a nice little hint you can see there. So I'm going to define two different search tools. I'm going to define a search web tool. I'll use Tavily Search for that. So this is a very useful search service. You set your Tavily API key, and then you can use it. And what we're going to do is hit Tavily with a question that's in our graph state, get docs back, and we're just going to format them in kind of a nice way and write them back to state context. We're writing them back as a list because, again, we look at our key, and it's a list. So there we go. We'll do the same thing with Wikipedia. Again, we'll just define this Wikipedia loader, we'll call it with question, and then we'll format the output, write it to context. So you can see these two nodes are going to write to the same key in our state, and that's fine because our key has a reducer, and we're going to run these in parallel. Then we're going to pass it to answer, which will take the context and answer a question based on the context. Let's draw a graph out here. So there we go. We start, we search the web, we search Wikipedia, we do those in parallel. We write both of those results to the same context key like we talked about. And then our answer generation grabs from context, grabs the question, formats a prompt with those, passes it to an LLM right here, gets an answer, writes that answer back out to state. So I can run it pretty easily. Let's ask a question about NVIDIA, the GPU company, and we can see the result. So this is a good practical use case for parallelization. For example, you want to retrieve information from multiple sources and aggregate it in a particular key, in this case context, and use that later for answer generation using an LLM. So let's interact with this graph using the LangGraph API. We have our graph with parallelization parallel, and they're writing to the same channel or key. You need to use a reducer that can aggregate those updates. We talked a lot about custom reducers. We talked a lot about reducers in general. So let's just do something simple. Let's just define state with a reducer that will just add updates to a list. And now we're going to draw that same graph. Here we go. So we're going to fan out. We'll fan back in. So now nodes B and C will be updating this state key. But because we have a reducer, all these state updates will just be appended to the list. So let's give this a shot, make sure it works. Very nice. So we can see we just get this list of elements, and we're able to run steps B and C in parallel, because even though they're writing to the same channel or key, we have a reducer that handles those updates and just appends them to the list. So the key point to remember is when you're doing parallel node operations and you're writing to the same key or channel in your state, just be very careful and make sure you're using a reducer that can actually handle those simultaneous updates. Now let's walk through another common architecture in parallelization. We'll go ahead and draw a graph out here. We'll modify it slightly. We're going to show two branches here. Now one branch has 2 steps and the other only has 1. So what's going to happen? What you're going to see is that even though steps B and C will be run roughly at the same time, that is, they're the first step in each branch, we will wait to run D until everything in this other branch is completed. Now let's go ahead and see that right now. Nice. So we can look at the final state list, and what we can see is first A writes the state, then B writes the state, then C writes the state, and then B2 writes the state. So even though we ran C, we don't go ahead and run D. We wait for everything in this other branch to finish, because these are all run, that is B, B2, and C, are all run as part of the same overall step. Okay? So you get B, C, and B2 all updated before D updates the state. So it's just an important point to remember that when you have parallelization, these parallel branches of your graph are run as part of the same step, and we will wait until they all finish before running D when they fan back into. So let's look at the state after our graph ran. We have A, B, C, B2, and then D. So you might ask, well, why is C coming before B2? Okay, they run as part of the same step. So you can see B here, C here, B2 here. And the answer is, this order of updates is actually set by the graph. So LangGraph decides how to order these updates when they're within the same step. You don't have control over that. But what if you want to customize that? So we can do that pretty easily using a custom reducer. Let's define a reducer that's actually just going to sort the values in our state after each update. So it's pretty simple here. You can see we basically perform the concatenation, and then we just sort the values in the list. So it's pretty simple. So recall the ordering above was B, C, then B2. And now we're going to find that same graph. Cool. Let's run it. And now you can see A, B, B2, C, D, because our reducer actually sorts the values as they're added. So even though by default, we don't have the ability to control the ordering of these updates within the same step here, we do if we supply a reducer that will control or manage the order of those updates as we make them in the state value. So let's pull all these threads together into a realistic example, which we're actually going to end up using a bit later as well. So it's kind of a nice little precursor. So I'm going to define an LLM. I'll use OpenAI just like we've been before, but of course you can use any model you care about. I'm going to find a really simple graph here. So here's my state. It's going to have question, answer, and then context. So you're going to see context is a list, and I have this add operator, which means we're going to append to it, okay? So this gives you a clue that this context thing is probably what I'm going to be writing to in my parallel nodes. So that's just a nice little hint you can see there. So I'm going to find 2 different search tools. I'm going to find a search web tool. I'll use Tavily Search for that. So this is a very useful search service. You set your Tavily API key, and then you can use it. And what we're going to do is hit Tavily with a question that's in our graph state, get docs back, and we're just going to format them in kind of a nice way and write them back to state context. We're writing that back as a list because, again, we look at our key, and it's a list. So there we go. We'll do the same thing with Wikipedia. Again, we'll just... So there we go. We'll do the same thing with Wikipedia. Again, we'll just define this Wikipedia loader. We'll call it with question, and then we'll format the output, write it to context. So you can see these 2 nodes are going to write to the same key in our state, and that's fine because our key has a reducer. And we're going to run these in parallel. Then we're going to pass it to answer, which will take the context and answer a question based on the context. Let's draw a graph out here. So there we go. We start. We search the web, we search Wikipedia, we do those in parallel. We write both of those results to the same context key like we talked about. And then our answer generation grabs from context, grabs the question, formats a prompt with those, passes it to an LLM right here, gets an answer, writes that answer back out to state. So I can run it pretty easily. Let's ask a question about NVIDIA, the GPU company, and we can see the result. So this is a good practical use case for parallelization. For example, you want to retrieve information from multiple sources and aggregate it in a particular key, in this case context, and use that later for answer generation using an LLM. So let's interact with this graph using the LangGraph API. we have our graph with parallelization deployed to Studio locally. We can interact with it via the SDK. Just apply the URL and the assistant ID. So we pass in a question just like before. We create a new thread. And if you recall, each event we run stream has this data object, which is just the state. So all we're going to do is, as we're iterating through our graph and it's producing state updates, let's just go ahead and get answer. And we'll only return answer. That's really all we care about, right? We're not going to return intermediate updates. So we could, of course, we add to context here, for example. We could print those, but let's just print the final answer in this particular case. We run it, and there's our answer. So we can also look at this in Studio to see some of those intermediate outputs. So now we're in Studio, we can see our graph here. Let's just open up our inputs. Let's just go ahead and ask a question. How are NVIDIA 2024 earnings? Let's have a look. So now we can see we're going to each of our sources. We're doing web search, and we're searching Wikipedia. And this is pretty cool. So we get a whole bunch of information in our contexts, and we get our final answer. We're building up to a multi-agent research assistant that ties together all the modules in this course. And to build that, we just covered parallelization, which is an important controllability topic. And now we're going to cover subgraphs, which is another important controllability topic. So subgraphs allow you to create and manage different states within different parts of your graph. And this is really useful in multi-agent systems, like teams of agents that have their own state. So let's just consider a toy example. I have a system that accepts logs. It does two separate things. It summarizes them. It finds failure modes in them. And I want to perform these two operations in two separate subgraphs. So here's really the key thing to understand and think about. How does the parent graph, or in my case, the telemetry graph, connect with or communicate with the two subgraphs in terms of state, right? And likewise, how do the subgraphs communicate back to the parent graph? In short, this is done with overlapping keys. That's the key concept to understand. So here's a toy example from below. My entry graph, or my parent, has a key docs. I want both subgraphs to have access to docs. All I have to do is just add that key to the state of each subgraph. Easy enough. I want my parent to also access like the reports from each of the subgraphs so it can return them in the end. All I need to do is just have the report keys present in my parent state. So you can see the subgraphs can have their own state keys like summary or failures that we don't care about in the overall parent state. But as long as the key things I want to communicate between the parent and the subgraphs are present in both places, they can effectively talk. So in this case, docs, I want to communicate to my subgraphs, just make sure the key is overlapping. And I want the report, summary report, failure report, to be accessible to my parent, just make sure those are overlapping. That's really the key idea in constructing subgraphs, and we'll walk through that in detail right now. So let's actually make this concrete. First, I'm going to define what a log looks like. This is just a type dict, so nice and simple. Now let's define my subgraphs. So we kind of talked about it previously. Here's my failure analysis subgraph. It's going to have some state here. And I'm going to specify an output schema for the state. We'll talk about why that's interesting a little bit later. But we talked about that in a prior section. And what this does, this simply sets the output schema of the subgraph is only going to contain information that I really care about servicing back to the user at the end. Okay. Now this contains all the internal information I want available in this subgraph. So let's just draw this out and see what it looks like. So there we go. It's very simple. We get the failures, we generate a summary, and we end. And these are all just toy functions. It doesn't matter. It's just to illustrate the concepts. So there'd be some toy function that, takes in the logs and isolates the failures and then looks at the failures and generates a summary. Okay, so that's all that's going on here. So there we go. That is our failure analysis subgraph. Now we also have this summarization subgraph. And again, we're going to define our summarization state and our summarization output state. We're going to have this generate summary, which again is just a toy node here. Here's a summary generated, writes back out to summary. And we have the send to Slack, which will, it's just, again, a toy function sends to Slack. Let's draw that out. Nice. Okay. So to add these subgraphs to our parent graph, all we need to do is this. First, let's define our parent graph state. Now you're going to see something interesting. Here's our input. Here are the cleaned logs, which are going to be passed to our subgraphs. These are what we want to surface to the user. So this failure analysis summary is produced in the failure analysis subgraph. This report is produced in the question summarization subgraph. Process logs are produced by both subgraphs. So in this case, I want a reducer because both subgraphs will be writing to the same key, process logs. Cool. Now you're going to see something kind of weird. why does cleaned logs have a reducer? This is just the input to each subgraph. So let's go back and look at that quickly. If I go back to my subgraphs, you can see they both use cleaned logs. It's just a list of logs, right? And that makes sense. We're going to get logs in our kind of entry graph here. We're going to pass them to both the subgraphs. But why the reducer here? Why is that actually needed? So the interesting point is that both subgraphs' output state will contain all their keys, even if they're unmodified. So we're not actually modifying or returning explicitly cleaned logs. We're not updating it explicitly, but it is present in the state of each subgraph, and it will be returned by each subgraph to our entry graph. And because of that, unless there is a reducer, that can cause a collision in our state key or state channel. So there's a really simple way we address that, which is that we used the output state schemas. So if you go back to our subgraphs, we defined this output state, which does not contain cleaned logs. Same up here, does not contain cleaned logs. And because we're using this output schema that doesn't contain cleaned logs, we won't expect any issue. Now, of course, they both do return process logs, okay? They both will write to that particular key, but that's fine because process logs has a reducer. So that's really the way to think about it. So actually, when we define our output state, or we find our overall state for the entry graph, clean logs does not need a reducer because it's not present in the output schema of each subgraph. And we're just going to add this one simple clean logs node here, and let's put it all together. Nice. So we're going to start. We're going to go to clean logs, and then we're going to run both of these in parallel, and then we're going to end. So let's go ahead and try that out. We'll take two dummy logs. We will pass them in, and everything runs. Very nice. So one other nice thing about subgraphs is they make your traces much more readable, particularly if you have large graphs with many important subcomponents. I'll show you that right now. So I'm in Langsmith and I'm looking at the trace of this subgraph right now, and you'll see something immediately that's pretty nice. The two subgraphs are encapsulated here, and they're collapsible. So I can open this up and look at what's happening under the hood. I can look at the various steps of this particular subgraph, likewise of the second subgraph, but they are nicely contained here. And if you imagine I have a complex system with many components, I can easily collapse the common subgraphs together and kind of open them up and drill into them, but then close them back down when I want to look at other parts of the system. So it makes your traces a lot more readable when you're working with large and complex graphs. We're building up to a multi-agent research system that ties together all the modules of this course. And to build this, we've been discussing a few LangGraph controllability topics. We covered parallelization and subgraphs. Now we're going to talk a little bit about MapReduce. So, as before, we're going to use Langsmith or tracing. And let's kind of lay out what MapReduce is. So MapReduce is basically an efficient task decomposition and parallel processing method. And it has two phases. One is what we call map phase. So that is take some task, break it into a bunch of subtasks, and do them all in parallel. Then the reduce is basically aggregate the results from all those parallelized subtasks and bring them back together. That's the main intuition. So here's a toy example that we're going to kick off. In the map phase, we're going to create a set of jokes about some topic. Reduce phase, we'll pick the best one. It's a really simple toy example. So here we'll just set up a few prompts. We'll set up a prompt for generate a list of subjects related to some topic that the user provides. Then we're going to have a prompt, basically, hey, create a joke for each subject. And we'll have a third prompt to select the best one out of the list. Okay, so that's kind of the setup of the problem.
இமேஜ் வரலையா? அதான் டாட் ஜேபிஜின்னு வந்தால் தானே வரும். ஜேபிஜி பிஎன்ஜிலாம் வரும். அது ஆன்லைனில் மாற்றலாம். எப்படி டவுன்லோட் பண்ணுற? மொபைல் அப்படியே டவுன்லோட் பண்ணுறேன். அதே ஆப் இங்கே வருமேடா. அதே என்ன டவுன்லோட் இருக்கும்? இன்ஸ்டாகிராம் டவுன்லோட் ஏதாச்சும் இருக்கு? அதேமாரி இதில் ஆன்லைன்லேயே இருக்கும் பாரு. இந்த யூஆர்எல் போட்டால் இங்கேயே டவுன்லோட் ஆயிரும். அதுதான் நீ மாற்றணும். டபிள்யூபின்னு அப்லோட் பண்ணுறான். இது வரும். இதை வந்து கன்வெர்ட் பண்ணிக்கலாம். இல்லைன்னா நீ என்ன பண்ண, டபிள்யூஇபி டு ஜேபிஜின்னு போட்டால் வரும்.
Let's talk a little bit about state and kind of how we're going to lay this out. So subjects and best joke are just two schemas that we're going to use, and you'll see a little bit later why this is very useful. Basically, it's going to be used with our LLM to produce structured outputs that adhere to these schemas. One of them is going to be a list of subjects. One of them is going to be the ID or index of the best joke from the resulting list of overall jokes we've made. Now, the most important one that's interesting is this overall state. This will contain the topic provided by the user. It'll contain subjects, which is a list of subjects we'll produce using this schema. Now, this is really the one to watch. This jokes, you can see it has a reducer on it that will append to the list. And what's happening here is we're going to fan out or map to a bunch of nodes that will produce jokes, and they're all going to write to this same list. So this list is kind of going to be the aggregation for all of the individual map nodes, jokes, and then we can use that list later to select the best one. So let's talk through the individual pieces now. This is just generate topics. So we take in state, we will grab the topic from state, form a prompt from that, and run it with our model. And again, we're actually using this with structured outputs method, which is very convenient. It allows you to produce a structured output from an LLM. We talked about a bit about this previously. Adhering to a specified schema. So this subject schema we define up here, and it's just going to be a list of strings. So it basically constrains the output to be of a particular type, which is very important here because we want this response to be a list. So we can go ahead and run that. Cool. Now here is where we're going to do really all the work. We now have this subjects list that lives in state. Now this send API in LangGraph is really the magical piece here. So what's going to happen is we have this list in state. You can see subjects. Now all we need to do is iterate through that list. And for every element in that list, for every subject in that list, we can use send to send it to a particular node. And you can see we have this generate joke node, which we'll define in a little bit. It can take in that subject, and it can do some work on that subject. In particular here, it'll generate a joke. And you're going to see very briefly, we can write that back out to this jokes key, which can append to our list using this add reducer. So this send API is really convenient for at least two reasons. One is that this list can be arbitrarily long. So this could be any number of subjects, and it'll automatically spawn a generate joke node, effectively, for every element in that list, and run generate joke. So that's one. It's very flexible in how many of these you can kind of spool up in your graph, which is really nice. We don't have to manually create all those edges. It'll automatically generate them all for us based upon the size of this list here of subjects. The other cool thing is we can pass arbitrary things in. So this subjects key is in the generate joke state, which we'll define very briefly. But that state can contain anything we want, and we can just simply plumb it in here. It's very flexible. It doesn't need to adhere to what we see here as the overall state. So this generate joke node that we're mapping to could have any state we want, and we can arbitrarily write to it in this via this send API. So let me show you that in particular. We're going to find that generate joke node right here, and it has its own joke state, right? In this case, it's only the subject, which we write to right here, but it could be anything, which is actually quite nice. So you can actually decouple the state of your mapped node from your overall graph state. And actually, we're going to be doing that when we kind of go and build our final assistant. Again, we're going to use structured outputs here. So basically, we're just going to have the LLM produce a joke, and it's just going to be a string based upon the prompt. The prompt is here. Again, we have that joke prompt we format with the subject that we pass. We get the joke, and we return it. Now, see something a little bit subtle here. We return jokes. We're writing this back out to our key here in the overall state, this jokes key. And again, we're passing it as a list so that it is indeed appended to our overall jokes list. That's it. So those are the key things to understand about the map step, which uses the send API here. And this is just the generate joke node that has its own state, and that will be duplicated arbitrarily via the send API, which is quite nice, based upon the length of the list of subjects. Now, the reduce phase, best joke selection, is really simple. All we need to do
பேமெண்ட் இருக்கும் பாரு
now is
ஃபீச்சர் தான்.
we have jokes written to state now as a list from here, and we just join them all into a single list, single string, and we pass them to our best joke prompt. And again, we just asked an LLM to pick the best one. This will respond with the index, if you recall. The best joke schema here is just an int, indicating an index value. So this returns an index, and that's really it. We just index that jokes list with the ID of the best one. Very simple. And return it. So it's pretty nice. Now let's try to compile that and see what happens. There we go. So we generate our topics. This is a list. Now here's the send. No, this is actually very interesting. This dotted line indicates a conditional edge. So you can see we apply add conditional edge, generate topics, continue to jokes, goes to generate joke. Now this continue to jokes is defined right here. That's this edge that uses a send API. So this, again, sends from, as we defined it down here, generate topics to generate joke, and it'll spawn up some number of generate joke nodes based upon the length of the topics that we want to generate a joke for. So that's really the new piece to recognize here. This is effectively the map step. And then those all go to best joke. So best joke, like we just saw, receives that
போர்ட்டல இருக்குது மட்டும்
list of jokes that the map step produces, and it picks the best one, updates the state with the best one, and that's what we get out. So we can see this all running. There it is. So we can see generate topics. There's a list of topics. Here is the jokes, and here is the best joke. So this is a great example to also look at in LangSmith. Now I have my LangSmith open. Here is this trace. And let's walk through it step by step. First we ran generate topics. Let's look at that. So here's the generated topics: lion, elephant, dolphin, penguin, given the entry topic of animals. Now I can expand this, and I can see this continue to jokes. Remember, this is that conditional edge that contained the send API. Let's look at what happened here. So this is the key point. You pass in this list of subjects, and it creates, basically, a bunch of calls to the generate jokes node that pass each of the subjects from that list in. That is quite nice. So it automates that parallelization for us. Now we can see those 4 generate joke nodes run. That's great. And this is going to be kind of as you expect. It's basically just going to generate a joke about the topic passed in. Lion, it performs a tool call to structure the output according to what we specify as a joke, and it's just like a string. And we can see, each of these is kind of identically laid out with different topics. And then we have this best joke, which, very simply, we can look at the call here. Here is our prompt. Here's a bunch of jokes about animals. Here's the ID of the one it likes the best. And then the graph goes ahead and returns the joke ID2 from this list as the best joke, and then we finish. So let's show this in Studio for one further illustration to really bring this home. So this is the same graph we've been working with. Pass in the topic, animals. Now we generate a list of subjects. That's cool. This is, so let's just walk through it. Generate a list of subjects. Each subject, we run this map step, generate a joke for each one. Boom. So we have 4 jokes generated, 1 for each subject. That's great. And then this reduce phase goes and selects the best one. In this case, it selects one particular joke. So I can even rerun this, and let's pause it here. Okay, we'll create an interrupt. I'll create a new thread. Just go back to my MapReduce graph. I'm adding an interrupt here. There it is. Animals. Generate topics. Now we're paused. Okay, so let's just look at this carefully. What's going on? We generate our subjects. Here's our 4 subjects. That send API automatically then spools up 4 different joke nodes, right? 1 for each of our subjects. And this is really nice. It does this all for us, right? We didn't actually draw this out in the graph. That send API takes care of it for us. Now let's just go continue. There we go. They all generate jokes in parallel, and that's very fast, obviously. And there we go. We go ahead and generate the best joke, picks the best one, and we end. So this is a nice way to kind of see MapReduce working visually, and I encourage you to play with it using mapreduce.py in the repository. Let's pull together the threads of memory, human loop, and controllability in a realistic, interesting multi-agent system that's capable of open-ended research. So research is often laborious, it's often offloaded to analysts, and AI can really help with this. But just raw LLMs are often poorly suited to real-world workflows or decision-making because A, you may want to provide specific sources for research, and B, you may want a specific output format, for example, reports that actually aid in high-quality decision-making. So we'll build a system that can do all that. It can automate it for us, and it can do it on any task we give it. First, source selection. We're going to give this system access to arbitrary sources. For this, we'll use a few different web search tools, but you can actually customize this. We're going to use a planning process where we'll take a topic given by the user, we will break that up into some set of subtopics, and assign an AI analyst to each subtopic. We'll use human in the loop to refine those subtopics. Then we're going to orchestrate a dialogue between each of our analysts and an expert that has access to the sources. So this is going to be like an AI role play where the analyst will ask questions, the expert will answer questions. That'll be a multi-turn conversation that we'll capture. We'll pull all those conversations together in a parallelized process. So we'll run them all in parallel. We'll use MapReduce to basically bring the results together at the end. And we'll finally synthesize it into a final report. So flow will look like this. We create some analysts based upon user-provided topic. Human feedback refines them. We then kick off research automation. Each analyst conducts research in parallel with an expert that has access to external sources. And then the reduce phase brings all those independent research results together into a final report. So that's our overall flow. Let's just set things up, define an LLM. We'll use LangSmith retracing like before. We'll log to this project. Now let's just build the analyst generation graph first, and we'll show how human loop is really helpful here. So here's our analyst schema. You can see each analyst will just have an affiliation, a role, a description of what they want to focus on. And this is just the list of analysts. And this is the state we'll use just for this subgraph to kind of experiment and play with it in isolation. So here's some instructions to create our analysts. And here's the overall topic. Here is optional human feedback, which will come in through human in the loop. Define the most interesting themes based on the topic. And create this number of analysts. That's really it. So this is where structured output comes in. We'll call LLM with structured output and pass perspectives. So remember that perspective schema is just a list of analysts. So what happens is the LLM will produce a list of analysts that will focus on subtopics of our theme, and each analyst adheres to this schema, which is very useful, as we'll see later. So this human feedback is a no-op node where we're going to interject human feedback. And this should continue is where we're going to basically look, hey, is there human feedback in the state? If there is, go back to create analysts, and if there's not, we end. That's really it. So let's make sure we've defined everything. Run that. Run this. Cool, we can see our graph right here. We start, create our analysts, go to human feedback, and we're going to pause here. See this interrupt before? We're going to pause at the human feedback node, await feedback. If we pass in any feedback, we'll go back and recreate analysts and start again. So this is actually really important because we want to make sure that the analysts we create have the right focus areas before the whole heavyweight research phase starts. This is really intuitive. It's kind of how you would think about any kind of research. If you have an analyst or a team of analysts, you make sure their scope is set correctly before they go do all the work. That's the intuition here. Let's test this out. Create 3 analysts. Here's our topic related to LangGraph. We'll create a new thread. And let's kick this off. Cool. This creates 3 initial analysts for us. You can see they adhere to our schema, which is pretty cool. Now we can get our state. We can see that the next state is human feedback. So now we're at the human feedback node. We're awaiting human feedback. So here's where I can do the state update, pass it as human feedback to basically run it as that node. Now let's say add in someone from a startup entrepreneurial perspective. Okay, so make sure I have an entrepreneur in there. I update the state. Now I just continue, pass none with the thread ID. The state's been updated as a human feedback node. Let's run it. Cool. So now I can see I have 3 new analysts. There it is. Alex Johnson is the founder of a tech startup. Good. No further feedback. Finish. Get our final state. Confirm we're done. Print out our final analysts. There we go. Alex Johnson's the entrepreneur, and we have an academic. We have a tech corporation, like a kind of a big company perspective. So nice. This is the first step of our graph, the analyst generation phase with human feedback. Now let's talk about the interview. So the interview is going to be
அப்படிதான் இருக்கு. பொண்டாட்டி வந்து செய்வா பாரு, தக்காளி சோறு இல்லாம நெய் சோறு இல்லாம பிரியாணி வந்து செய்வா பாரு. என்ன செய்யறேன்னு நானும் பாரு. தான் போவேன். ஏன்டாக்கா அதுக்கு ஈரல் கஷ்டப்படுறேன். ஏன் ஈரலுக்கு பேட்டு ரவீந்திர பாக்குறது செட்டாதாப்பா